Module 1, Lecture C, ML Problem Types. By the end of this lecture, you will be able to describe supervised, unsupervised, and reinforcement learning in intuitive terms, match simple problem descriptions to the appropriate machine learning category, and identify the type of data and feedback signal required for each learning category. Supervised Learning Basics. Inputs and labels. In supervised learning, a model is trained using examples where each input is paired with a correct answer, called a label. The inputs are the data we provide, and the labels are the outcomes we want the model to predict, such as an image of a digit and the number it represents. By seeing many of these input and label pairs, the model adjusts itself to better match inputs to the right labels. It is called supervised because the labels act like a teacher, guiding the model during training. In supervised learning, we want to discover how inputs relate to labels so we can make predictions. Inputs can be many types of data, such as numbers, text, images, or audio. And labels are the outcomes we want to predict, like whether a patient has a disease or whether an email is spam. The model is trained by studying many examples of input and label pairs and learning patterns that connect them. This training process depends on having known, labeled examples to guide the learning. In supervised learning, both the input data and the labels must be high quality for the model to perform well. Noisy or incomplete inputs make it hard for the model to learn useful patterns, even if the labels are correct. Incorrect labels, in turn, cause the model to produce unreliable predictions. For instance, if house prices are recorded incorrectly or important features like location are missing, the model's understanding of housing values will be distorted. Therefore, carefully choosing informative inputs and ensuring accurate labels is essential for effective model training. Classification and regression. In supervised learning, tasks are usually divided into classification and regression. Classification assigns inputs to discrete categories, such as deciding whether an email is spam or not spam. Regression predicts numeric values on a continuous scale, like estimating the price of a house. Both rely on labeled examples, but classification uses category labels while regression uses numeric targets. And recognizing this difference helps you choose the right method for your prediction problem. To tell classification and regression apart, focus on the type of output the model produces. If the task is to choose from a fixed set of categories, such as labeling emails as spam or important, or grouping patients by risk level, it is classification. If the task is to predict a numeric value, such as a ride fare or the number of students who will enroll, it is regression. Classification deals with discrete categories, while regression deals with continuous numerical outputs that can vary widely. In many real-world systems, classification and regression are applied to the same data for different goals. For example, a health app might use age and heart rate to predict a numeric value like resting heart rate with regression, or to classify someone as at risk or not at risk for a condition. Choosing whether a problem is best framed as classification or regression is crucial because it affects how you prepare data, how you measure performance, and how you make decisions based on the results. Building an intuitive sense for this distinction helps you quickly recognize the structure of new problems and select the right supervised learning method. Loan approval prediction. In supervised learning, a bank can use past loan data to train a model that predicts whether to approve new loan applications. The historical records include an applicant features such as age, income, and credit score, along with labels that show whether each loan was approved and repaid. By learning from these input and label pairs, the model captures patterns that link applicant characteristics to outcomes. Once trained, it can generalize from past decisions to make informed predictions for future applicants. In supervised learning for loan decisions, the algorithm is trained on past applicants and their outcomes. and it adjusts its internal parameters so its predictions match what actually happened. When it predicts approval but similar applicants were rejected or defaulted, it updates to become more cautious in those cases. Over many examples, it learns numerical patterns, such as low income combined with high debt often leading to default, and stable employment with timely payments indicating successful repayment. Using these learned patterns, the model can then predict whether to approve or reject new applicants, or estimate how likely they are to repay a loan. In this loan approval example, supervised learning uses past cases where each application is labeled with whether it was approved or not. The model learns a mapping from applicant features to outcomes, so it can reproduce or improve these decisions, such as predicting approval, estimating risk, or suggesting interest rates. Once trained, it can make real-time predictions, like flagging high-risk applications. The same idea applies in other areas, such as predicting hospital readmissions, detecting fraud, or forecasting subscription cancellations, always by learning patterns from labeled examples to support accurate and consistent future decisions. Finding hidden groups. Input-only scenarios. When choosing a machine learning approach, a key question is whether your data has labels that indicate the correct answers. If you only have raw data, such as news articles without topic tags or customer purchase histories without value labels, you are not predicting known outcomes. Instead, you are trying to discover patterns or structure within the data itself. In this input-only situation, unsupervised learning is the appropriate choice, rather than supervised or reinforcement learning. To categorize a machine learning problem, focus on how the data and goals are described. If you have examples with known labels and want to predict those labels for new cases, you are dealing with supervised learning. If your data has no reliable labels and your goal is to discover patterns or group similar items, that is an unsupervised learning problem. For example, if a company has song data with untrusted user tags and wants to group songs based only on their acoustic features, they are trying to uncover natural structure in the data rather than predict specific labels. Reinforcement learning involves an agent that learns by taking actions, receiving feedback, and improving through trial and error over sequences of decisions. In contrast, unsupervised learning works with static datasets that have no actions or rewards. Its goal is to discover patterns or structure directly from the input data, such as grouping research articles or organizing photos by similarity without using labels. The key idea is that unsupervised learning uncovers structure from the inputs alone, rather than predicting outcomes or optimizing rewards. Discovering hidden structure. Discovering hidden structure refers to working with many examples that have no labels telling us what is right or wrong. We might have raw data, such as purchase histories or health records, and suspect there are underlying patterns. In this setting, an algorithm analyzes the unlabeled data and groups it into meaningful clusters or patterns that are not obvious at first glance. The goal is not to predict specific outcomes, but to uncover the natural organization already present in the data. When a task focuses on finding groupings or patterns without labels, it is using methods that rely only on the input data itself. Some data problems focus on exploring hidden structure rather than making predictions. In these cases, people want to uncover natural groupings or patterns in the data without predefined labels, such as finding different types of customers, disease subtypes, or listening patterns. The goal is to let algorithms suggest structures like clusters that help us make sense of complex information. When tasks are described in this way, they are about discovering hidden structure in the data. Hidden structure tasks are different from other machine learning problems that use labeled outcomes. For example, predicting customer churn uses known labels, so it is not a hidden structure problem. In contrast, finding customer types without prior labels or grouping news articles into themes without predefined categories are examples of discovering hidden structure. To recognize these problems, check whether labels are known. If they are not, and the goal is to group or uncover patterns, it is a hidden structure task. Customer grouping example. Imagine an online retailer with millions of customers and rich data on how often they shop, how much they spend, what they buy, how they react to discounts, and how long they have been customers, but without labels that describe their type, such as bargain hunter or loyal high spender. The goal is to use this unlabeled data to discover natural groupings of customers so the marketing team can design targeted strategies. This situation illustrates unsupervised learning, where you feed the algorithm data without predefined categories and let it uncover hidden patterns and clusters on its own. In this scenario, you use unsupervised learning, such as clustering, to group customers with similar behaviors based on their data. The algorithm might find groups like frequent small spenders, occasional big spenders, or shoppers who buy only during major sales. However, the algorithm only forms the clusters. It does not explain what they mean. You and your team must interpret each group, assign meaningful labels, and decide how to act on them, such as offering special access to loyal high spenders or discounts to more price-sensitive customers. In unsupervised learning, we work with raw, unlabeled data to discover hidden patterns or structures. The model does not receive feedback about the correct group for each data point, so it must find natural clusters on its own. This approach is useful for tasks like guiding marketing or product decisions, segmenting patients in healthcare, or organizing media content. Whenever the goal is to identify meaningful groupings in unlabeled data, unsupervised learning is the appropriate method. Reinforcement learning basics. Agent, environment, interaction. In reinforcement learning, an agent learns by continuously interacting with its environment instead of using a fixed data set. At each moment, the environment is in some state that the agent observes and feeds into its decision-making policy to choose an action. The environment then moves to a new state and returns a reward that reflects how effective that action was. This cycle of observing, acting, and receiving feedback repeats over time, creating a changing stream of data rather than the static examples used in supervised learning. In reinforcement learning, the data is a sequence of states, actions, and rewards unfolding over time, rather than simple input-output pairs. The impact of an action may not appear right away, and a choice that seems neutral at first can lead to large rewards later. Because feedback is delayed and often noisy, the agent must learn to connect future rewards back to earlier decisions. For example, a warehouse robot learns from its ongoing sensor data and the rewards it receives for efficient navigation and task completion instead of training on a fixed dataset. In reinforcement learning, an agent's actions change future states of the environment, creating a feedback loop rather than working with fixed data. The agent actively shapes the data it observes through its decisions. For instance, in traffic control, adjusting light timings alters future traffic flow and the states the agent will see. Rewards, such as reduced congestion, guide the agent to improve its policy over time. Through this ongoing interaction, the agent learns to better predict and influence its environment. Rewards and actions. In reinforcement learning, an agent learns through a cycle of observing the environment, choosing actions, and receiving rewards that indicate how good those actions were. The reward is a simple number that can be positive, 0, or negative, but it does not tell the agent exactly what to do. This feedback can be noisy or delayed, so the agent must gradually discover which actions tend to produce better outcomes. Over time, by recognizing patterns in the rewards, the agent adjusts its behavior to favor actions that lead to higher total reward. In reinforcement learning, actions are the choices an agent makes to affect its environment, such as selecting from discrete options or adjusting continuous values. By trying different actions and observing the rewards that follow, the agent gradually learns which actions are most beneficial in different situations. Over time, it builds an internal understanding of the link between actions and rewards, even when that link is indirect or delayed. In reinforcement learning, the agent builds its own data by interacting with the environment, taking actions, and observing the resulting states and rewards rather than relying on a fixed, labeled dataset. The reward signal is often sparse and delayed, so the agent may need to perform many actions before it can judge how effective they were. This setup reflects complex real-world situations where feedback is not immediate. The agent's main objective is to learn a strategy that maximizes long-term rewards, carefully balancing short-term gains against future outcomes. Python code, rewards, and actions. This script demonstrates how reinforcement learning uses rewards and actions within a simple grid world environment. It focuses on how the agent receives feedback signals from the environment, rather than on the internal details of the model. By observing how rewards guide the agent's choices in this tiny example, you can better understand the role of data feedback in reinforcement learning. We begin by importing a library for randomness so we can generate random numbers and choices, which lets us simulate unpredictable behavior in the grid world. We also import a numerical computing library to work efficiently with arrays. By setting a random seed through this library, we make sure our random operations can be reproduced. These steps prepare the tools we need to define the grid world and simulate how the agent interacts with it. We set a fixed or deterministic seed for both the standard random module and NumPy's random module so that the random numbers they produce are the same every time the code runs. This makes the behavior of the program predictable instead of changing from run to run. Having consistent random outputs is important for reproducing experiments and for debugging because it lets you reliably repeat and analyze results. We define a simple grid world with 2 rows and 3 columns as the environment for our agent. Within this grid, we specify a single goal state. The goal is located in the top right corner at row 0 and column 2. This position is the target the agent tries to reach during its exploration of the grid. In this grid world environment, the agent has a set of possible actions that let it move around the grid. These actions are defined as 4 directions: left, right, up, and down. At each step, the agent chooses one of these discrete actions to navigate the space. Defining actions in this structured way makes it clear how the agent can interact with the environment and supports the simulation of its movement and decision-making. The step function is used to compute the next state and the reward based on the current state and the chosen action. It begins by breaking the current state into a row and a column, which represent the agent's position in the grid. With this position information, the function can determine how the agent moves when an action is taken and what reward should result from that move. The code updates the position based on whether the action is to move left or right, while keeping the position inside the grid. For a left move, it reduces the column index, but uses a maximum check so the index never goes below 0, preventing movement past the left edge. For a right move, it increases the column index, but uses a minimum check so the index never exceeds the last column, preventing movement past the right edge. In this way, the position is adjusted according to the action, while always staying within the grid boundaries. When the action is up, the program moves the agent 1 row higher in the grid, but prevents the row index from going below 0, so the agent cannot move past the top edge. When the action is down, it moves the agent 1 row lower, but prevents the index from exceeding the last row, so the agent cannot move past the bottom edge. In both cases, the agent moves a single step within the grid while staying inside the allowed boundaries. The code updates the agent's next state by forming a pair of values for the current row and column. This pair represents the agent's new position on the grid after it takes an action. These updated coordinates are then used to track how far the agent has moved through the environment. They are also used to calculate the reward the agent receives based on its new position. The code assigns a reward based on whether the next state is the goal. If the agent reaches the goal state, it receives a reward of 1, marking success. If it does not reach the goal, it receives a small negative reward of -0.1. This small penalty for non-goal states encourages the agent to reach the goal as efficiently as possible. This function returns two key pieces of information: the next state and the reward. The next state is the agent's new position in the grid after it takes an action. The reward indicates whether the agent has reached the goal or not. Together, these outputs are essential for updating the agent's understanding of the environment and guiding its future decisions. A random policy function selects actions purely by chance. It receives the current state as input, but does not use it, which is why the state is intentionally ignored. Instead, the function simply chooses one action at random from the options left, right, up, and down. This means each action is equally likely, creating a simple and unbiased way to explore the environment. We configure the simulation to run for 5 episodes, meaning the agent will explore the environment 5 separate times. For each episode, we also set a maximum of 6 steps, which limits how long the agent can act before the episode ends. These settings keep each run short and controlled, making it easier to observe and compare the agent's behavior across multiple trials without the process continuing indefinitely. We start by creating an empty list called trajectories to store what happens in each episode of the simulation. For every step, this list records the current state, the action taken, the reward received, and the next state. By collecting these sequences over time, we can later examine how the agent behaves and how the environment responds. This stored data is essential for analyzing and improving the agent's performance. We simulate multiple episodes in which the agent explores the grid world environment. For each episode, we loop once through this process, starting by setting the agent's state to a fixed starting position, 1 row down in the first column. We then create an empty list to record the steps taken during that episode. This list stores each state, the action chosen, the reward received, and the resulting next state, allowing us to track the agent's entire path through the environment. In each episode, the agent runs through a fixed number of steps. At every step, it picks an action using a random policy that chooses uniformly from all available actions. Using this action and the current state, the step function returns the next state and the reward. Repeating this process simulates the agent's interaction with the environment, letting it explore different states and observe the rewards it receives. The code records each step of the episode by adding a tuple to the episode steps list that includes the current state, the action taken, the reward received, and the next state. This creates a log of the agent's journey through the environment. After logging, the current state is set to the next state, so the agent is correctly positioned for the following step. This update keeps track of the agent's movement as it navigates the grid world. In this part of the code, we check whether the agent's current state is the same as the goal state. If they match, we immediately stop the loop, which means the episode ends early. We do this because once the goal is reached, the objective has been met, and there is no reason to continue exploring further. The code stores the list of steps from each episode in a larger collection of all episodes. This means we keep a record of every sequence of states, actions, rewards, and resulting states the agent experiences. By appending each episode's steps to the trajectories list, we can later review, analyze, or summarize how the agent behaved across many episodes. The code generates a brief summary for each episode describing what actions were taken and what rewards were received. It begins by printing a short header that tells the user that episode summaries will follow. This header makes it clear that the focus is on the sequence of actions and the reward feedback for each episode. For each episode, we loop through its trajectory using an index, so we can track that episode separately. As we process the steps in an episode, we add up all the reward values from those steps. This total reward gives us a single, clear measure of how successful the agent was in that episode. In other words, the sum of rewards across the episode reflects the overall performance of the agent for that run. The code looks at the first and last steps in an episode by taking the first and final elements from the list of episode steps. The initial step shows where the episode began, and the final step shows where it ended. Together, these 2 points help summarize the overall trajectory of the agent's actions and rewards during the episode. The print statement provides a brief summary of each simulation episode. It reports the episode number, adjusted so counting starts at 1 instead of 0, then shows the starting state taken from the first step of the trajectory and the ending state taken from the last step. It also displays the total reward collected during the episode, rounded to 2 decimal places. This concise summary makes it easy to quickly assess the agent's performance in each episode by focusing on the initial state, final state, and overall reward. This script simulates a simple grid world to demonstrate basic reinforcement learning ideas. An agent starts at a fixed position and can move up, down, left, or right, trying to reach a target cell. Reaching the goal gives a positive reward, while every other move has a small penalty. The agent does not learn. It follows a random policy, choosing each action with equal probability. Over 5 episodes, the script records the agent's moves and rewards, ending each episode when the goal is reached or a step limit is hit, and then prints the start and end positions and total reward to show how actions lead to feedback signals. Game-playing agent. In game-playing agents, games provide a clear setting to study how reinforcement learning uses data and feedback. An agent learning a game like tic-tac-toe or chess observes the current board state and chooses an action, such as moving a piece. Unlike supervised learning, it does not receive labeled examples of the correct move. Instead, it learns from delayed rewards based on the game's outcome, like winning or losing, and sometimes from smaller rewards for certain moves. Over time, this reward feedback helps the agent discover which actions lead to better results. In this game scenario, the agent continually observes a state, chooses an action, and receives a reward over time. The state is what the agent currently perceives. The action is the move it decides to make, and the reward is a numerical score that reflects how effective that move was, either right away or later. For example, in a video game, the state could include positions and health, actions could be movements or item use, and rewards could be points or progress. By repeatedly acting and observing the environment's responses over many play sessions, the agent generates its own learning data and gradually improves its strategy to choose actions that maximize future rewards. In reinforcement learning, feedback is not given as explicit labels like in supervised learning. Instead, an agent learns by trying actions and later receiving rewards, such as game outcomes or scores, which are often sparse and delayed. This delay makes it hard to know which actions were actually helpful, so the agent must rely on its history of interactions. Over time, by exploring different strategies, observing states, and tracking rewards, it learns a policy that maps situations to actions to achieve better long-term results in tasks like games, robotics, or resource management. In this lecture, you learn to describe supervised, unsupervised, and reinforcement learning in intuitive terms. Match simple problem descriptions to the appropriate machine learning category. And Identify the type of data and feedback signal required for each learning category. In the next module, Module 2, we will go over data and features. Thank you for your attention. See you all in the next lecture.